We actually recorded last time, but I'm not sure if I actually uploaded the video. Let me see if I can find that video somewhere here. See, that would have been the 9th. That's the 8th, so that's not it. That's a different one. Here it is. All right. Upload a video really quick before I forget. All right. Okay, so, wrong one again. Okay, here we go. So we're recording, we're ready to go. Yesterday we started off chapter 20, correct? Started talking about electrical current and what it is. Here we calculated the number of electrons moving through a calculator. We talked about drift velocity, conduction of electricity and heat we talked about. Okay, so I guess this is about where we left off, is right after we started talking about drift velocity. So let's go ahead and start here again. So remember yesterday we talked about the fact that there is this this random movement of electrons inside of conductors as electricity is moving in a current, and that the overall direction that the electrons move is opposite the direction of the current. The current's always the other way, as is the electric field inside the conductor that's driving the current. And that this drift velocity is the average velocity of these charges, even though they might be moving, sideways, backwards, whatever. Their overall average velocity is forward. And that drift velocity is actually not exactly the same as the movement of the signal, you could imagine, you could think of it as. So you can have a drift velocity that is forward, but the result of the current can actually reach the other side of the circuit very quickly because of kind of the domino effect. And here they talk about that right here. So that while the drift velocity can actually be, so the maximum velocity of electrons can be very, very fast. The maximum velocity of electrons can be super fast because they're so small. It can be like millions of meters per second even. Not necessarily likely that all of them are going to be that, but one of them could be doing that while the other one's going much slower. So these things can really, you can make an electron go the speed of light really easily. Well, very close to the speed of light, not the speed of light, but very close. Because it's so small, put an electric field, it just takes off. However, because it bumps into other electrons and bumps into other atoms and does other things, it bounces around a lot. The average drift velocity will actually become quite low, but the signal velocity can be extremely high. Again, very close to the speed of light, because of the domino effect. This one pushes, this one pushes, this one pushes, and all of a sudden it's um, kind of like dominoes falling. It just can happen extremely quickly. And then because of this, because of all these things going on, these collisions, and there's just a lot of interaction going on, this actually creates heat. There's actually a loss of energy in the electron as it bounces to and fro, back and forth. Every time a charge accelerates, it loses energy in some way. And some of that energy is transported out of the metal in terms of heat, by some amount of heat. And that heat, of course, heats up the metal, heats up whatever the current flows through. All right, so here they actually put together an expression that relates the drift velocity to the current. So what they do is they start with this volume of the wire. Here's the wire, and we take this front area and this back area, and we have these charges moving through, and their average forward velocity is this drift velocity. So the distance here is traveled in, you can travel this distance at this velocity in this time according to just a standard, kinematic equation, x equals v times t, velocity times time. And so that's a distance now. And if you multiply that distance by the cross-sectional area of that distance, you get the volume of this cylinder here. And that volume can be used to calculate how much charge is in there. And that change in charge is now A times X times the number of charges in that volume times the amount of charge per charge in that volume. So now we've got an expression for delta Q that includes Q and A and X. And of course, X rather has the drift velocity. And so we can replace that X with the drift velocity. And in fact, you can actually say that just X over delta T is the drift velocity. And so you get the drift velocity in there. So the current is equal to the number of charges times the amount of charge per charge times the times the cross-sectional area of the wire times the drift velocity. And we're going to use that in this equation, in this example right here, where we're going to calculate the drift velocity in a common wire that's carrying 20 amps, has a diameter of 2.053 millimeters, so it's 12 gauge copper. And that's pretty normal wiring for a house. Pretty much all the wiring that goes to your outlets in your house is going to be 12 gauge, unless it's an outlet that carries a lot of current, like the one going to your oven or something will have more higher gauge. It's actually a lower number gauge, so 10 gauge is a bigger wire. But anyway, the point is that this is going through this type of wire. It's also copper wire, so tell us the density of copper there. Then we're going to calculate the drift velocity using the equation that we've got here. So the current is 20 amps, of course. The charge is going to be the charge of an electron because that's what's moving. The area of the cross section, we're going to use the pi r squared for the area of a circle. So we get half of this diameter and square it, multiply by pi. Density of copper. This is actually going to give us the number of atoms per mole, which will tell us the number of free electrons in this copper, because there's one free electron per copper atom. So we got to figure out how many atoms there are. And that's for the number n, which is the number of charges available, wherever that is in the equation right there. That's the n. So we use this the atomic mass of copper and the density of copper and Avogadro's number per mole, and that'll tell us the number of atoms per cubic meter, the n. So there's your moles, there's your charge, well, that's the number of free electrons per atom. Here is the 1 mole for every 63.54 grams. So they're essentially telling you how much mass is in each mole. Convert that to kilograms, and then you use your 8.8, which is actually the density of copper. Multiply that all together, and you get 8.342 times 10 to the 28 free electrons per meter cubed of copper. Other metals have different numbers of free electrons. But anyway, multiply all these together. They're calculating the area, drift. Then you can plug in all that stuff and get the drift velocity. Turns out it's negative 4.53 times 10 to the minus 4 meters per second. The negative is on there is because the current is going one way, the charges are going the other way. So that just shows that it's the opposite direction of the current. But you can see that's not very fast. 4 times 10 to the minus 4 is 0.5 millimeter per second. So not very fast. But the signal moves much, much faster. Signal moves close to the speed of light. Okay, so now we've learned what current is about. We're going to go on to Ohm's law from our friend, the German physicist Georg Simon Ohm. So what Ohm figured out is that the current and the voltage are proportional in a particular situation. So let's say that we have a light bulb that we're driving current through. If we increase the voltage going through the light bulb, we will increase the current going through the light bulb, or vice versa. If we increase the current going through the light bulb, that increases the voltage across the light bulb. So so these things are directly related to each other in any particular circuit or situation. And the other thing that he discovered is that the current is inversely proportional to the resistance in the circuit. So if you start changing the resistance, you increase the resistance, then the current will actually go down. Or if you decrease the resistance, the current will go up if you keep the voltage constant. And from those two relationships, he combined the two and came up with this law that actually works very well, that the current is equal to the potential difference across the circuit, or the voltage across the circuit, divided by the resistance in the circuit, where resistance has to do with how much the particular material the circuit is made of does not allow electrons to go through it. That's what resistance is. Resistance is how much it resists those electrons as they try to go through it. So we actually now come up with the idea of resistance. Turns out that if you solve this equation for resistance, you find that resistance is equal to volts divided by amps. And we call that the ohm. 1 ohm is 1 volt divided by amps, or amperes. So that's resistant, the ohm. And that's this letter here is, this symbol here is the Greek letter, the capital Greek letter for omega. It's the equivalent of W, I guess, in our alphabet, but it's the last letter in the Greek alphabet. They don't have a Z, so that's omega, the ohms. So here's our very simple circuit. We're going to start you off with a circuit diagram. We have a battery. Remember, the positive end is the longer side, the negative end is the shorter side. We have a resistor, and we know that in a very simple circuit like this we've seen before, where it just has this single loop going on, we know that the current is going to come out of the positive side and go around towards the negative side. So they go ahead and label that current. And in this very simple circuit, and in any circuit really, the current passing through this resistor will equal the potential across the resistor divided by the resistance of the resistor. And this resistor could be made of lots of different things. You can actually make a resistor out of copper. Copper does not have a very high resistance. So you'll make very, very small resistors if you make them out of copper. However, you can make resistors out of other things like ceramic. There are a lot of resistors have ceramic. A lot of resistors are made of metals that have been you could think of them as corroded, but oxidized metals, oxidized things. Semiconductors you can make resistors out of. You can make all kinds of resistors out there. Different ways to make resistance happen in a circuit. But in any case, this has some resistance. And so the amount of resistance it has determines how much current goes through. If it has a lower resistance, then more current will go through for this particular voltage. And here is an example of this kind of a circuit. An automobile headlight is essentially a resistor in a circuit with a battery. Pretty simple stuff. So you have 2.5 amps flowing and a 12 volt potential across it. When they say applied to it, it means it's across the resistance. So you measure a 12-volt distance difference from one side to the other side of the headlight. And we rearrange this to calculate the current. Actually, we're finding the resistance. We're going to rearrange this to calculate the resistance. So we rearrange to find the resistance. That equals V over I now. So the resistance is 12 over 2.5, which turns out to be 4.8 ohms of resistance, which is a very small resistance. Anything under like 100 ohms is considered a pretty small resistance. 4.8 is pretty typical for a light bulb. Light bulb is essentially just a wire that glows when it gets hot, when there's current going through it. So they're usually pretty low resistance kinds of things. The interesting thing is that when you turn on a light bulb, it is very, the wire is quite cold. It's the same temperature as the room, but as it heats up and it starts to glow, it gets very, very hot, like hot enough that you could cut right through your finger with it. That's hot. It would just melt right through your finger pretty easily if you could touch the filament. So and that includes your bones. That's how hot it gets. It gets really hot. So but the thing is that as it gets hotter, the resistance actually increases. And so when you first turn it on, a lot of current runs through the light bulb. And then as it stays on and gets hot, less and less current flows through it, which is interesting because almost every time a light bulb burns out, it's when you first turn it on and when that big surge of current goes through it. And that's actually what kills light bulbs. But when you pop a light bulb, it's because it has a bunch of current going through it and the light bulb can't handle that current. So, and light bulbs get less and less, they can handle that kind of current less and less as they get older and older, because these light bulbs get so hot, and incandescent light bulbs get so hot that they literally are boiling the metal off of the filament. So the metal actually gets thinner and thinner and thinner the longer you burn an old incandescent style light bulb. And then eventually it's just so thin that when you try to put that current through it, it just breaks it. It just heats it up and pops it really quickly. So the long.
I have a question about this.
Sorry, what's that?
I have a question about this.
Yeah, go ahead.
So the battery, so like this is a car battery they're talking about with the headlights.
Sure.
And so the colder the battery is, does that affect the battery, or is it just because it's trying to?
Yes, the cold affects the battery in a different way. For the most part, metals resistance goes down when they're cold and goes up when they're hot. But batteries are not necessarily a metal all the way through. So I think we talked about batteries at one point, but let me, good night, give me my tools back. There we go. But a battery in its, on the inside, a battery is not metal. So a battery is essentially some kind of container that has two metal rods stuck into it somehow. And they don't have to be rods. For example, in a AA battery, it's usually some foil in it. But it usually has some piece of metal in it somehow, in some way. And then inside here, there's usually some kind of an acid. So in a battery, like a AA battery, it's an alkaline acid. In a car battery, it's usually a let's see, what kind of acid is it in the car battery? I think it's like muriatic, or I don't remember what kind of acid it is. It's some kind of acid. It's a pretty strong acid in a car battery. But this becomes a chemical kind of reaction in here. So chemistry is going on in here to create ions which can flow from anode to cathode, cathode to anode. And that's what creates the potential difference in the battery. And it also is what allows the current to flow through the battery. So temperature affects batteries differently because chemical processes are affected differently by temperature. Generally, a chemical process speeds up and improves its efficiency when the temperature goes up. and it is not as good when the temperature goes down for chemistry. In metal, it's different. It's the exact opposite. Usually the resistance goes down when you have a low temperature, so that the electricity goes through it better. And then it goes up when you have high temperature. So it's actually kind of you have two opposite things happening with temperature. With temperature, the current flows better through the circuit, but worse through the battery, right? And the exact opposite thing when the temperature goes up. It travels worse through the metal and better through the battery when the temperature goes up, right? So the other problem is with temperature and the battery is, as the temperature goes up in chemical situations, reactivity also goes up. And so the battery chemicals will react with other things like oxygen or water or any other kind of contaminants that might be present. And so that contaminates the battery, and then eventually the battery won't work at all because the chemistry has been contaminated over time. And that's what happens when you have to replace the battery eventually, because contaminants get in there and mess it up. And so they fix the battery by draining all that acid out, cleaning the electrodes, and then replacing it with clean acid, with new acid. And that's how they rebuild those car batteries. And car batteries are rebuilt. That's why you return them to the store, because they just rebuild them and resell them again. So you might be using like Elvis's battery from 1976. You don't know. It's possible.
Okay.
Did that answer your question?
Yeah, it,
Yeah, so there's a little give and take in that particular thing. All right, let's see, where were we? Coming down here. Oh, so here we can actually talk about how voltage is actually measured using a voltmeter. A voltmeter is a device that that has some electronics in it, but they're pretty simple electronics for the most part. It has a very high resistance to it, so almost no current will pass through it. It will allow a little bit of current to go through it, but that little bit of current has a big, it creates a big reaction in the voltmeter. And it's because of some electromagnetism kind of stuff going on inside the voltmeter, or it's because of something going on inside of a microchip in a more modern voltmeter. But voltmeters are designed to have no current going through them, because if the current goes through them, that will actually affect the current going through this resistor, because current, there's only so much of it. If you have some of it taking a turn off this way, then it won't all be going through here, and then that will affect the voltage across the resistor. But voltmeters are always used to measure the drop on voltage across some kind of element, or the voltage difference in between 2 points in a circuit. So in this particular case, we want to know the drop in voltage across the resistor, or the change in voltage across the resistor. So we put our leads right here and here. And guess what? Those are connected to something with a very low resistance here and here. And so we're going to actually be measuring the voltage across the battery terminals when we put them right here. It's going to be a very little difference between the voltage here difference and the voltage difference here. And that's pretty much always the case. We have an 18-volt battery here. We're going to get an 18-volt difference if we just have one resistor lined up with it. All right. Remember also that voltage is measuring the amount of energy per unit charge. So when we put our voltmeter into the circuit like this, and we measure it at 18 volts, that tells us that we have 18 joules per coulomb of energy for every bit of charge going through that circuit. So it tells us something about the energy of the charges moving through the circuit. And energy is conserved in electronics actually fairly well. It's conserved pretty well. And so at least I guess a better way of saying it's conserved pretty well is it's very easy to track it through the circuit. Energy can leave the circuit very easily and get lost in the form of heat, because resistances heat up in the circuit. Other things can heat up in the circuit as well. But it's fairly easy to track it and see where it's going and know how it's leaving the circuit. So we use a conservation of energy. But conservation of energy, as long as you keep all the charges going around your circuit, the conservation of energy is just about conservation of voltage. So if you have 18 volts at one end of the circuit and you go all the way back around back to that same point of the circuit, you should have the same amount of voltage. In other words, the voltage difference between this point and this point is zero because nothing has changed. The potential doesn't change if you go from one point all the way around back to that same point. And that becomes a very important idea in electronics as we try to evaluate electrical circuits, conservation of energy. Here you can do a little bit of exploration. You can change the voltage by adding batteries here, and then you can change the resistance. They're essentially changing the density of whatever material this is, so that blocks more current, and you can see how the current changes as it does that. There's a better one. There's a better one that FET made. I can't remember if they still have it here. I should check it, take a look at it. Yeah, this one, I like this one better. So in this one, you can make simple circuits. So if I put a battery in here, and then I put a wire on this end of the battery, it connects it. And I put another wire in on this end of the battery to connect it. And then I can put it up here and I can put in a resistor or a light bulb. I'm going to put a light bulb in. So I connect the light bulb like this. And then it shows the direction of the electrons flowing. The electrons flow out the negative end of the battery around through the light bulb and back towards the positive of the battery. And you can actually ask it to show you which direction the current is going. So I can do this. Now it's showing me the current goes the other way, but the electrons are actually flowing this way, right? And I like that. And then you can actually show that, let's see, I can't remember how to disconnect something. Tap circuit element to edit. There we go, cut it, there we go. So I'm going to disconnect it. You can see that if you don't have a complete circuit or a complete circle, then nothing can flow. The electrons have nowhere to go here. And I'm going to add a battery here. Why not? And see what happens. If I add a battery, then I've actually increased the potential difference because this battery has like 1.2 volts. This one has another 1.2 volts. So this is like, the batteries are kind of like pumps. They can actually, you put more of them in a row, they can make this stuff go faster. You could think of it as more current and a higher voltage because it's more current. It comes from that higher voltage, and you get more light because there's more energy. More voltage means more energy. And then you can bring in your voltmeter here and you can measure a voltage difference like between here and here, 18 volts. And guess what? If I switch them, if I put them both on the same side, it's 0 volts because it's the same point in the circuit. There's no difference in voltage there. But if I switch them, it's negative 18 volts because it knows there's definitely a direction to current, right? And if I go across one of these batteries, these are actually 9-volt batteries, not 1.2. But if I go back across both, it's 18, right? And you can do, so that's what you do with voltage. And voltmeters are actually pretty hard to break. Current meter is different. With a current meter, you actually have to let the current flow through the device. So in this case, they have this little ring here that you let the current flow through. And you can see that it's 1.8 amps here, and it's 1.8 amps here, and it's 1.8 amps here. But that makes sense, I think, because the current has nowhere else to go but through this circuit. So if I measure it here and I measure it here, it has to be the same, because how could it be any different? It couldn't branch off and go anywhere. There's only one loop to this circuit. So, you know, that's another way that we can measure the current is using what this is called an ammeter. This other one is called an induction meter, but this one's called an ammeter. So this one we actually have to put into the circuit to allow the circuit to flow through it. And then it can measure that current because all the current has to go through it so it knows exactly how much current is going. So take that. Oh, oops. I just closed it. But I like that one better because it actually shows the flow of current a little bit better, I think. I actually want to go back to it again really quick. So if we put our battery in here again and then some wires. So a light bulb is kind of like a resistor, right? So I'm going to put my light bulb in here and I'm going to connect it. And you can see that it's flowing here, and we could check the current going through. So we'll do that. And I'm actually going to have you all using this to do some electronics labs once we get labs started here. So we can see we have a current of 0.9 amps through this light bulb right now. But now I'm going to go ahead and cut this one, and I'm going to add in a resistor. The light bulb's like a resistor. I'm going to add more of a resistor. What do you think is going to happen to the current now? Anybody? Bueller. Okay, the current can do three things. It can either go up, go down, or stay the same. Who thinks it's going to go up if we add a resistance into here? Anybody? Raise your hand on, raise your hand, give me a thumbs up or thumbs down on the Zoom. You can do that in Zoom, can't you? I think so. Thumbs up or thumbs down, it's going to go up. Everybody vote. Is everybody voting? Can everybody hear me?
I can hear you.
Okay. I need a thumbs up and thumbs down from everybody. We've got 3 students on right now. Give me a thumbs up or thumbs down. Current going to go up or down if I put more resistance in here?
Down.
Think it's going to go down. Okay. Anybody else?
Down as well.
Okay. We have a consensus for down there. Let's see what happens. It does go down. And of course, the current goes down. The light also goes down. And it turns out if we actually measured the voltage across this, the voltage would also be down across the light bulb. So some of the voltage dropped across the light bulb, some of the voltage dropped across the resistor. The current meter has almost no resistance, so there's no voltage drop there. But the current does go down when we increase the resistance, just like in the other example, but you don't really see the current flowing very well in that one. So definitely it goes down, and that's Ohm's law for you. All right. So it turns out that just about any material has resistance. There are a few materials that have zero resistance in certain situations. We call them superconductors, and we're going to talk about those later. But for just about any material, you can calculate the amount of resistance using some of the geometry of the material and some of the properties of the material. So if your material is, if you have a current flowing through a material in this direction, you actually need to know the cross-sectional area of the material. Doesn't matter what the shape is, as long as you can figure out the cross-sectional area. You need to know how long the current is going to flow through the material, so the length of the material it's going to flow through. And then you need to know this thing that we call the resistivity, which is something that is measured about the material, which is how much resistance that particular material has per unit length, essentially. And that thing is called, that is the rho here. That's not a P, it's a rho for resistivity. And so the resistance of a particular piece of material that has length L, cross-sectional area A, and resistivity rho is rho times L over A. Quite simple. And so you can actually calculate the resistance of wires this way. if you have a silver wire, you use this for the row, and let's say that the cross-sectional area is 1 millimeter squared, and the length is 10 meters. You plug in the length, 10 meters, divided by 1 millimeter squared, or 0.0001 for your area. And then you multiply by this resistivity here, and you'll get the resistance of that piece of wire. It will be a very low number, but it will give you some resistance. Here you have the resistivities of several conductors. Silver 1.59 times 10 to the 8, copper 1.72. The lower the resistivity, the better the conductor it is. So silver is a great conductor. Copper is also a great conductor, but not as good as silver. So why do we use copper in our electronics instead of silver? Well, the truth is we actually do use silver in much of our electronics. That's one of the reasons that silver is quite expensive, because it is used in a lot of electronics. But we use copper in a lot of our electronics because it's not quite as rare, it's not quite as hard to find as silver is. Gold, also a pretty good conductor, not as good as these two, but gold has an advantage over these two metals in that it doesn't react with oxygen and oxidize. And most of our electronics are in an oxygen atmosphere because that's where we live. So some of your high-end electronics that you really want to work well all the time are actually using gold in their wiring. And that's one of the reasons that very expensive electronics are very expensive, is because of the gold in them. Aluminum, also a fairly good conductor. The downside of aluminum is that it melts at a fairly low temperature. So all these things heat up when they get current going through them. But silver and copper do not melt at very low temperatures, and gold doesn't melt at a very low temperature. But aluminum does. Aluminum melts at like 600 degrees Celsius, which means you can melt aluminum at home on your stoves in some cases. Your stovetop almost gets to that temperature. So it's almost possible to melt aluminum in your house. Tungsten, not such a good conductor. However, tungsten melts at extremely high temperatures. So it's really good for making the filament in your light bulbs, which is what they normally use for filaments in light bulbs, is tungsten. Iron, you can see here, not a great conductor. Platinum, not a great conductor. Steel, not a great conductor. One of the great things about platinum, however, is that platinum's resistance doesn't change very much with temperature. It has a very stable temperature change curve. And so very expensive thermometers are actually made with platinum with current running through them. So they put a current through a platinum wire, and then they put that wire in the environment they want to measure the temperature of. The platinum changes its resistance, so it changes the current going through it. That measured change in current is used to calculate the temperature. And a platinum resistance temperature sensor can cost $25,000. And platinum is a very expensive metal, very, very rare, and very useful in many, many ways. So steel, lead, all these things, not very good conductors. Their resistivity is going way up. And then you have semiconductors like carbon. Pure carbon includes things like, pencil lead is pretty much pure carbon. So are diamonds, that kind of thing. But it can change. Coal has a different one. The coal is mostly carbon, but not all carbon. These things have pretty high resistivities, but it changes sometimes when you apply electricity to them. For example, silicon has a pretty low resistivity when it has a voltage applied across it, a voltage difference across it, but a very high resistivity when there's no voltage across it. And then there's insulators, which have a really high resistivity because they really don't like things to go through them. So now you can use the equation for resistance now to calculate the diameter of a wire, of a filament or something, from the resistivity of the material, the length of the diameter, and the resistance of the overall wire. And they're doing things like that in this example, using that equation. And then finally, we get to this last equation in this section, I think. I think it's the last equation in this section. The last equation in this section is how resistance changes with temperature. So if you have the original resistance of a wire at zero temperature, at 0 degrees Celsius, I believe it is what R0 is measured at. And then you put it into this equation with this thing called alpha, and the change in temperature has to be measured in Celsius. Then you can calculate the final resistance at a different temperature. That alpha is right here for all these materials. This is called the coefficient of the heat coefficient. What is it called? Can't remember what it's called. Doesn't matter what it's called, I guess. But anyway, it's this, let's see. Those are the resistivities, yeah. So this is yeah. Okay, here it is, alpha. But I don't know what they call it. I don't remember what it's called. But anyway, it's just the temperature coefficient of resistivity. And you have these numbers here for each one. As you can see that they're very similar for some of these metals, but there is some variance. And then, of course, for semiconductors, you have different ones as well. This one's quite large. These two are quite large for semiconductors. But here they give an example where a filament is going to change temperature as it heats up, in a light bulb, and then you want to calculate the final resistance using the initial resistance and that change in temperature. It's just plugging in numbers in the end. So that's all I have for you today. We're starting to learn more about resistance, and we'll be getting on to more about electrical circuits next time. I hope that you have a great day and a great weekend. Remember tomorrow, oh, I didn't tell you about tomorrow. Tomorrow I have to go to a meeting. So I'm not going to be able to visit with you in Valentine, and I also won't be able to have class because my meeting starts at 2 o'clock and goes till like 3:15 or something. So we're not going to be able to meet tomorrow, but still feel free to email or whatever if you have questions. Have a good weekend. Hopefully you won't get frozen out, and we'll see you on Monday.
All right, thanks. You have a good weekend too.
Thank you.